Hey, nice to see you back again. How did you go with those topics from Part 1 in Pearson's? These are all from Chapter 1 of Pearson's textbook, and I've decided to break them down into a few more parts. Instead of just having 1 and 2, we'll have 1, 2, 3 and 4, and just look at smaller pieces of revision work. What have we got here? Well, Honey Mouse is going to hit exponents now. Exponents are indices, or there is yet another word, isn't there, which you might remember for this sort of notation. It's also called powers. And what is it? Well, it's a handy way of writing a number multiplied by itself several times. Like, what do we call this? We call this 2 to the 5th. So it's really a bit of mathematical language which involves an abbreviated form. We don't write out all the 2's multiplied together. Rather, we summarise it as 2 to the 5th. And you'll notice up here, the textbook, Pearson's now has started to use a notation. We're talking about a real number being raised to a positive integral power, positive integer, because n is a member of z plus. You'll notice also that Pearson's uses a dot as equivalent form to timesing. We don't tend to use that these days because the dot could be confused with a decimal. But it is one of the forms that is commonly used. So we have actually 3 words for this abbreviated form: exponent, power or index. And they all mean the same thing in this context. Later on, we will look in mathematics at exponential functions. And an example of that would be y equals 2 to the x. And then we will look at also power functions. Something like y equals x to the 2 or x to the 3 or something. So there is a subtle difference. Here with exponential functions later on, the variable is the exponent or the power. And in power functions, to distinguish that difference, they've both got powers, but this time the variable is the base. The variable is what we call the base of the power expression. So later on we do make a distinction between the word exponent for that number up the top and power in those functions. So let's move on a little bit and have a look at some more notation. As I said, the IB really do like the notation. They like to see us using mathematical language. It's neater. So here we're saying in these rules below, we're dealing with A and B, which are real numbers. They could be positive or negative, but the powers that we're going to deal with in the rules below are all positive whole numbers. We're going to start there with our basic definitions. Now hopefully you've seen a lot of these from earlier work, but here we go. Let's have a look at them again. If you have some number raised to a power, m, and another number, or the same number raised to a different power, how many b's would all be lined up? You would have m plus n, wouldn't you? Just thinking of that, b by b by b, there might be m of them, and then b by b by b, n of them, all in a row, adding up all the b's, you'd have m plus n. So using it in x land, x squared by x to the 5th will be the same as x to the 7th. So multiplying, I don't like the word here multiplying like bases. I like the idea of multiplying expressions together which are powers of the same base. It implies, what do? You add or sum the powers. That's how we could interpret that. And if you had the number b raised to the m and divided by b to the n, if you thought about that along here, m b's over n b's is less here, so there's m of these and n of these, whatever that is. We could start cancelling. How many b's would be left in the top line? M take n, all in a row. So we get this rule now. So here we've got w to the 7th divided by w squared will be w to the 5th. Okay, subtraction of power. So dividing expressions which are powers of the same base from here, you would subtract the powers. So you can see how these rules work then. If you had a number raised to the m, that's m lots of b's all times together, and then you did it n times, how many could you add up all the b's? It would be n lots of m, or mn b's. So if we had 3 to the x squared, let's do that one over here. 3 to the x by 3 to the x, that's what squaring it means. You would add the powers x plus x, which is 3 to the 2x. Was there any need to go through all of that? We could have just said, we'll multiply the powers together. And then we could call 3 squared 9. A power raised to a power implies multiply the two powers together to get the total number of that base present in your final expression. The next two are fairly easy. The idea that if you have a power of two numbers multiplied together in a bracket, then you have to do that raising of the power to both the terms in the bracket. So it's a to the m by b to the n. So when we get this little doofy here, 4k all cubed because of the bracket, you've got a cube to 4 and cube to k. And cubing 4 is 64. So the power of a product is the power of each term in the product. Now I'm going to write that down over the next line as well, because when we have two things divided, all raised to a power, you do the same thing. It's the power of the top number over the power of the bottom number. So here in the example, it's y squared, must do the square to y, must do the square to the bottom part of the expression, the 3, and so you get 3 squared is 9. So the power of a product or a quotient is the power of each term. Must be done to each of them. Now there's something funny going on down here. Something funny going on here. How can we have a to the naught? How can you have a times itself no times? Well, it's not quite like that. Let's have a look at a cubed over a cubed. And we'll say a is not equal to naught. The reason we're going to say that is you can't divide by 0. In mathematics, there is no definition for division by 0. Let's first of all treat a cubed over a cubed by our power rules. Division is subtraction of powers. 3 take 3. That's where it came from. We've got this creature a to the naught through using the power rules that we've just developed. Can we decide what that should be then? What would be consistent with our mathematics? A cubed over a cubed, a number divided by itself gives 1 over 1 is 1, as long as a is not 0, because you can't divide top and bottom by 0 to cancel out. So that's where it came from. Can you see that the small beginnings, our desire to abbreviate repeated multiplication, has turned into quite an interesting area of mathematics? We're getting some other things happening here. Okay, well let's have a look at the next one. What's this? A to the neg n? How could you get a to the neg n? Well, can we play a bit? Let's play with a squared and divide by a cubed. According to the power rules, it's the top one minus the bottom. Hey, look at that. A to the neg 1. That's how you get a negative power. When you've got more a's in the bottom line or the denominator than in the top line. And what's it overall mean? Let's do this one and see if we can see what it means. Well, a squared was that and a cubed was that. So if we cancel those and that once, this comes to 1 on a. Aha. I think you can see now that a negative power means that you've got that number of a's still left in the bottom line, because it had more a's in the bottom line than in the top line. So it means 1 over. The winning number of A's are in the bottom line. So, gee, isn't this getting interesting? All right, I want to go over here. Pearson's got a good hint here. It's important to recognise the difference between this sort of expression and this one here. Can you see it? It's all to do with brackets. This one means we want to square all of neg3. That would be neg3 by neg3 would be plus 9, positive 9. This says square 3 and then make it negative. This is neg 9. Be careful, the calculator will do this to you. If you mean you want to square all of neg 3, you must enter into the calculator, whether it be a TI or a Casio, you must enter into the calculator the bracketed form. So bracketing that form then is neg 3 squared, which will give you positive 9. So it explains it all there, but we need to watch that when working with the calculators. Okay, let's come down a bit and see where these powers are leading us. It's an interesting journey. Okay, here's another interesting piece. You would have had this last year, where you have a rational power, a fraction as a power. What might that mean? Well, what about 3 to the half? Surely that can't mean anything. Oh yeah, 3 to the half by 3 to the half. What will you do? The bases are the same, so you'll add the powers. Half plus a half is 1. So 3 to the half is that number which multiplied by itself equals 3. You multiply 3 to the half by 3 to the half, and adding the powers you get 3 to the 1. Hey, that's the definition of the square root of 3. The number which multiplied by itself gives 3 is called the square root of 3. Therefore, a half power means the root, the square root. That's interesting. What about doing another one? What about something like 2 to the 1/3? If we multiply it by itself 3 times, 2 to 1/3, a third plus a third plus a third is 2 to the 1. Oh, 2 to the 1/3 is the number multiplied by itself 3 times equals 2. Oh, 2 to the 1/3 therefore must equal the cube root of 2. Because by definition, the number which multiplied by itself 3 times is the cube root. So we have some little examples over here. 36 to the half means the square root of 36, which is 6. Neg 27 to the 1/3. The 1/3 power means the cube root of neg 27, which would be neg 3. 1 over 81 to the quarter. The quarter means the 4th root of 81. What number multiplied by itself 4 times gives 81? Let's check it out. A third by a third by a third by a third. Yes, it's 1 on 81. Okay, so you can see it's really building up. And down here, can you see that if I had a power raised to another one, I multiply the powers together? So it's possible that one of those could be a fraction, like 1 on n. So what it would mean is b to the m, all to the 1 on n, means the nth root of b to the m. Or to make the working simpler, you might take the nth root first and then raise it to the power, because finding the root of a number is going to reduce the size of the numbers that you have to work with. So let's do that down here. Let's have a look at this little one here. 9 to the 3 over 2. Best probably thought of as the root of 9, all cubed. Think about the two parts. The denominator means the root, and then this is cubing it. The root of 9 is 3. 3 cubed then is 27. Getting quite interesting, isn't it? Let's do the next one. Neg 8 to the 5 over 3. Best thought of probably, let's do the root first. The cube root of neg 8 all to the 5th. What number multiplied by itself gives, so 3 times gives neg 8? It's neg 2. So neg 2 to the 5th is neg 32. Interesting combos. Should do this one over here, shouldn't we? 64 to the 5 on 6. Let's do the root first. It's the 6th root of 64. Can you think of a little number which multiplied by itself 6 times gives 64? You're right, it's 2. 2 to the 6 is 64. So this becomes 2 to the 5th, which is 32. See, it's becoming an interesting set of results now. Let's go down and have a look at some more. So here's the definition of rational exponents. Rational exponents means when you've got a ratio of integers, and so that's what we've just been doing there. So in other words, you can have a fraction. You can have a to the 3 on 2. And what we just established is that would mean the square root of a, doing that bottom part of the power exponent, and then cubing it. Okay, so you might like to pause the presentation now and have a go. I don't think I can get all these. Oh, I might be able to get them on the screen here. There we are. There are A through K up there. So pause the presentation now and have a go. And as I told you before, I'm going to include all the work solutions now so that you can see how to do them. Okay, so pause the presentation, have a look at those few up there. What have we got? We've got 11, I think. 11 little problems. Well, I'm coming back now to go through them. I wonder if you've checked them off here. Here we go. It's a cube, so I have to do it to every term. Cube all of them, and then a power raised to a power is to the 6. So just check those out. What's this one here now? Neg 2 to the neg 3. First of all, a negative means 1 over. So do that negative part of that power first. Remembering in this one, a to the neg n means 1 on a to the n. So I would follow Pearson's here and do the negative part of any exponent first by making it 1 over. Okay, a take 2 to the naught is 1. Hang on, we should put something in there. Provided that a is not equal to 2. Now you should watch that condition, because naught to the naught is not 1. It's based on a number divided by itself, and you can't have 0 there. So provided that, I put a is equal to 2, a is not equal to 2. So anything raised to the 0 will give 1 as long as that item, that expression can't be 0. Okay, so let's look at all this now. 3 cubed all to the half times 9 to the 3 over 4. Oh, lots of busy powers going on in there. Multiplying the cubed by a half, and then breaking, see that there, breaking 9 down to 3 squared, and then combining the powers. This is a very busy line here. Got to work with the product of powers here because it's a power raised to a power. Here's an interesting one. Notice that when we have 2 lots of bases, you keep the a's together. So look at what they've done here. The top line is a to the neg 2, take neg 5, and b to the 5, take 4. Or you could have done that a different way. B to the 4 on b to the 5. I probably would have suggested you go 4 take 5, which is neg 1. And that puts it in the bottom line as well. Hard one here. What would you do first of all? Well, what Pearson's has done is actually found what neg 32 is as a power of 5. And then when you multiply the 2 together, those cancel. Another way of doing that, of course, would be to say this is neg 32. Let's do the root of it first, the 5th root of that, and then raise it to the neg 4. The 5th root of neg 32 is neg 2, and raise it to the neg 4 is then going to give you 1 over 16. So that's another way in which you could do it. We'll just move this over here a bit, and we need to scrub this out. There we are, that's a bit better. Just put it over here. It's going to come to 1 on 16. So there are a few different ways you can do it. And notice I would be suggesting here not doing it this way. I would suggest you do the cube root first, and then simplify it. So here it is here. Reduce the size of the number first, do the cube root of 8 to get to 2, and then square it. So have a look through those. I'll just bring it down here so that you can mark them. Quite some interesting problems here. I don't really agree with this method here. I would like to see students go a plus b to the top line minus the bottom, a half take 1, which is a plus b to the neg a half, and then say that's 1 over a plus b to the half, which is 1 over root a plus b. Same answer, just looking at it slightly differently. Just notice that you can't split the root over a sum there, because you know that when you square a plus b, you don't get a squared plus b squared. Therefore, the root of a squared plus b squared is not equal to a plus b. You can't distribute the square root operation over a sum. Okay, what's this one here? The top power minus the bottom, but look out, the bottom line was negative. So it's 2, take neg 2 is 2 plus 2 is 4. Okay, so here's your rule. If you are doing the nth power of a sum, you cannot distribute it over each of them. Okay, there we are. But let's move on and see what other delights we've got in this area here. Well, here we are, a mixed bag of problems here. I think there's only 28. Yes, there they are, the 28, and it gives you some clues here. Now, I've got to start to get you ready for the papers. See how Pearson's here and here and here have suggested not using your GTC. Do not use graphics display calculator, because remember now, if you look back at the syllabus, paper 1 is a non-calculator paper. So you will have to do some mathematics in your head, some calculation in your head. It's a non-calculator paper. So you are going to be faced with things like, there it is, the 5th root of 32, being able to work that out as 2. We have to watch that now, because since 2008, the IB and standard level have had a calculator paper, paper 2, and a non-calculator paper in paper 1. So we do have to build up our skills with some numbers. Okay, so I'd like you to pause the presentation a minute. I'm going to just go down here and show you, and this time I won't do it as fast as I did it last time. We'll just go down to about there, I think, and so that you can mark the first 10. So you can, when you've done the first few, move the presentation on and mark them, then go back and do the rest. So I think if we come down there, we would have covered all of them. So I'll pause it there then, or bring it to just still format there, and then you will be able to mark those when you get to them. We've got to just toggle the presentation around a bit if you want to see the fully worked solutions. All right, well, you're back up here now and having a go there. Pause the presentation, maybe do the first half a dozen, go back and have a look at the solutions and so on. Checking your work as you go, because you want to make sure you're on the right track. Don't do a whole lot, only to find out that they're all wrong. All right, good luck with those. Let's move on now. And here we have a very, 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 very important use for the index or exponent or power form of a number. In your experience so far, you have probably had big numbers like this, because light goes so fast. Each second in 1 year it would travel that distance. Or what about the size of a molecule or an atom? Very, very big and very, very small numbers. And of course, you've seen this on the calculator. The calculator usually has a 10-digit display. So for this one over here, what's it going to write? Well, it runs out of room. So what does it write? It writes 9, hang on, we'll put it over on this side here. 9.460, we aren't out of room yet. 73047, what are we up to? I think that's it. No, one more. And that would be rounded to 6. And it puts e to the, what, 9. I think actually usually, I just rub that out, I think it goes e to the plus 9. Meaning that you really have to move the decimal here. So it's an abbreviated form. And what's this mean on the calculator? It means exponent 9. Or exponent of what? Exponent of 10. Or power of 10. So it's telling you this number is actually, let's get rid of that, this number is actually, having trouble with multiplication on that, the number is actually all of this over here. But it's going to put it like that and e to the plus 9. We don't ever use this technology symbol. It's important to use a power of 10. The e plus 9 stands for an exponent of 10, which is 9, but we write 10 to the 9. And that's called scientific or standard form. So let's do this one in here. So what is it? It's 5.60, 3 significant figures, times... Now, it isn't 5.6, it's actually way back here, the decimal. So we've got to count the number of places back it is. So how many zeros? 3, 6, 9, 12, 15, 18, 19, 20, 21, 22. So it's 10 to the neg 22. We've actually got to take the decimal, if it was a number between 1 and 10, 5.6, and move it back all these zeros. 3, 6, 9, 12, 15, 18, 21, 22. I've got a different number now. Hang on, we better check this. 3, 6, 9, 12, 15, 18, 21, 22, 23, 24 I make it this time. Oh, better watch that. By the 24. So I actually have to move that 24 places back from 5.60. So the convention, the way we usually do it, is we say we'll write the number as a number between 1 and 10 and then tell everybody where the decimal really is. So, you know, in the first one here, the decimal wasn't there, 9.4, it was way down the end. So we had to multiply by 10 to the 9. In this one, the decimal isn't 5.6, isn't in between the 5 and the 6, nowhere near as big a number as that. We actually have to divide that by 10 to the 24. So there's, again, Pearson using good mathematical notation. Don't get confused. All this is saying is scientific notation is a number between 1 and 10 multiplied by some power of 10 to adjust the decimal, to correctly place the decimal. We don't like lots of zeros in expressions. It makes it very, very busy here, all of that. Okay, so again it's about mathematical language here. Let's go down and have a look at some. Alright, here we go. Use scientific notation to calculate each of the following. Well, here the easiest way is to change the first number to standard form. That's a number between 1 and 10. Do you see? If we call this 6.4, we'd actually have to multiply it by 2, 3, 4, 10 to the 4th to get the decimal in the right place. And this one, if we said the decimal was there, 2.5, we'd have to multiply it or shift the decimal 9 places to the right. So the idea is to codify, if you like that word, or encode it as a number between 1 and 10. Remember this, number between 1 and 10 multiplied by a power of 10. So it's a neat way. And then, of course, here you can see your exponents to the rescue. that takes a lot of the zeros out of the problem. 10 to the 4 by 10 to the 9, there it is. We've just learnt that is 10 to the 13. So we reduce the size of the numbers we're working with, because most of them are zeros. Okay, let's look at the second one. Very small numbers, always a number between 1 and 10. This time times the power of 10. The power of 10 is going to be negative, because the decimal is actually way back there. 3, 6, 7 places back. And here if we call this 1.2, the decimal is way back 9 places. So it's 1.2 by 10 to the negative 9. Just remember, standard or scientific notation involves writing big or very small numbers as a number between 1 and 10 times the power of 10, so we're not writing heaps of zeros in. Okay, let's look at a cube root one. This is a big number to find the cube root of, but scientific notation to the rescue. 2.7, and how many decimal places do I have to come in here? Because it's way back there. It's 10 to the 10. And then I'm going to find what? The cube root of that. So it's a third power. So here, what is the way in which we could do this? We could say it's 27. So here, if we call this 27, then this is only 10 to the 9th. Let's use one of the 10s there to make that a 27. So it's 27 by 10 to the 9. And then if we raise it to the third power, it's the cube root of 27, which is 3, and the cube root of 10 to the 9, which is 10 cubed. We've actually been able to work out what looked like a horrible, horrible number. And we did that by actually using scientific or standard notation. So what's that last one? Quite useful. Are you ready to have a go? I think should let you loose on these. So these are all questions now which the idea is to make the expression neater or put in a standard or scientific form because it's got lots of zeros or numbers in there. So remember the standard form. You write it as a number between 1 and 10. So that's where you put the decimal. So you create a number between 1 and 10, and then you multiply by a power of 10 to show people where the decimal really is. Okay, so you might like to pause the presentation now and have a go. Let's come down and have a look at the solutions to these. Now, the graphics display calculator I've got here is a TI. In our work we'll be using a Casio, but you can still do the same thing. They have a note here about 3 significant figures, and significant figures are the number of figures of actual measurement rounded back. So you start counting the number of figures that have actually measured something. So here it's the first non-zero digit counting from the left. So if we have an example, let's have an example over here, 0.04278. Now this is a spacer, so the first figure that's actually significant or has made a measurement is the 4. So we would say here, this is 4.2. Now we're only allowed to use 3 figures, so we look at that one. It's 7, and because this is bigger than 5, we take the 7 up, so that's 8. By now, where's the decimal really? We're saying it's in there. No, it's across to the left 2 places. So 4.28 by 10 to the negative 2. Right, so here are your solutions. I think you'll probably be able to work your way through this, but rounding them off to 3 significant figures is the usual requirement in the IB standard level maths and in the high level as well, to use 3 significant figures. So don't forget to do that. Alright, so there are your solutions. It's if you work through the problems, you can come down, or as you do them, a few at a time, go back and spin back, toggle back and have a look at the solutions. So I'll just leave you with the ones at the top there and have a go. Here we are. Remembering you're trying to write the big number in a neater form, number between 1 and 10 times the power of 10, and usually it's 3 significant figures. So we get rid of a lot of the background noise, if you like, in a number, because quite often we can't measure to that degree of accuracy. So we're cutting out that background noise and making the number far easier to understand and work with. All right, so good luck with that. Now, I've got more delights for you coming up in revision topics. What are we up to? 2, and now we're going to go to 3 and 4. I'm trying to break that Pearson's chapter 1 down into more digestible pieces. And you don't actually have to do all of these exercises. Do enough to satisfy your needs. All right, so I hope you enjoy yourself. Get lots of practice in. You need these skills, very important skills. And it's cheers for now from me. I'll catch you in the next presentation.